Okay, so I wanted to give sort of a broad overview of beyond the standard model physics, but picking and choosing just some interesting topics that allow us to cover a range of things. Um, so one of the great advantages of studying physics beyond the standard model, or thinking about it, is that it gives you a new appreciation for the standard model itself. And so I found that by looking at physics beyond the standard model, I actually began to appreciate many of the special features, beautiful features of the standard model. And by thinking about the standard model, I hope you'll see it inspires us for how to go beyond the standard model. Okay. So, so before I'm going to lecture by actually writing on the screen, but I just wanted to give a quick introduction to what I'm going to talk about. And for that, I just prepared just 3 slides or 4 slides. Okay, so um, bear with me. Um, so one of the things that we're going to tackle, perhaps the major thing that we're going to think about, is why particle physics is so hierarchical. Um, so here I've sort of drawn on a mass scale many of the things that we have measured or know about from the point of view of the standard model and beyond. So you can think of this as a logarithmic scale of masses, and you can see that we'll talk about it, but we're going to talk about these scales, the Planck mass at super high energies, the gut scale, also at very high energies. If you go 15 orders of magnitude down from that, then you start to get the weak scale where we have the Higgs and the W and the Z and the top. Um, and we have these 3 generations that we see. And there's a lot of hierarchy just within the standard model. The masses of all the different quarks and leptons seem to be distributed in a very uh, sporadic or random way on the log scale. Okay. And then we know there is such a thing as dark matter, but exactly what mass is associated with its fundamental building blocks, we don't really know. You can see it could be anything over many orders of magnitude. But one thing we can see here is that particle physics is definitely very hierarchical. It ranges over many, many, many orders of magnitude. Of course, the photon and the graviton, as far as we know, are massless. Um, okay, so as I said, we're going to look for clues from the standard model itself as to how to understand some sort of mechanisms that would create such large hierarchies. From the quantum field theory point of view, if I get through all the material I want, and I may not, but the set of things that I'd like to focus on from a theoretical perspective are effective field theory, which I usually just write as EFT, the renormalization group, um, the importance of strong coupling, non-perturbative effects like confinement, conformal field theory, just a little bit about the ADS-CFT duality, extra dimensions of space-time, supersymmetry, and the importance of cosmological correlations. So that's sort of the theoretical side of the story I'm going to tell. Um, But then from the experimental side, the excitement of the field is that it ranges over so many different types of experiments that are still ongoing, um, like proton decay, precision measurements of the Higgs at the LHC, the searches for top anti-top quark resonances, searches for superpartners related to supersymmetry, uh, searches for dark matter passing through the Earth, indirect cosmic ray evidence for dark matter, flavor physics, electric dipole moment searches as probes of CP violation, the cosmic microwave background polarization and the search for B modes, uh, and large-scale galactic structure surveys. So this is ranging over an enormous body of experiments of every type, and yet they're all connected to thinking through the hierarchies that I just showed you. Okay, so all of these features of theory and experiment come together in just trying to understand why particle physics is as hierarchical as it appears to be. Okay. And just so you know where we're headed, last of the pre-prepared slides, here's the quick outline I had in mind. Again, going as far as I can till we run out of time. I just want to give perspective on quantum gravity and the Planck scale. I want to quickly give a very simple definition of the hierarchy problem, or I'm going to give a very simple definition of the hierarchy problem because I want to show solutions to it. And by seeing the solutions, you will have a better sense of what it means to have the problem in the first place, rather than speaking in a very precise language about the hierarchy problem. Okay. Then I want to discuss the chiral gauge theory structure of the standard model, which is part of the answer to why the particle physics can be so hierarchical. Going beyond the standard model, I wanted to start with grand unification and the scale of grand unified theories, or the GUT scale. In doing that, we'll quickly go through a few tools, theoretical tools like effective field theory, renormalization group. We'll study gauge coupling unification and the phenomenon of proton decay within GUTs. I then want to motivate composite Higgs theory, the idea that the Higgs is a composite and the phenomenology associated with that, as well as the related mechanisms of partial compositeness, which is a beautiful mechanism for generating hierarchies among the standard model fermions. In order to build models rather than just qualitative reasoning, I want to describe how ADS-CFT can be used to allow us to build models using higher dimensional space-time. And then if I have time, I want to talk a little bit about supersymmetry and its possible relation to so-called WIMP dark matter, but in particular, just this example of Higgsino dark matter. And then I want, if time permits, I'm not sure I'll get to it, but the idea, the ability, the possible ability to see grand unified theories, to see the highest energy scales, maybe many orders of magnitude above collider energies, by using cosmology. Okay, so that's the plan, and now I will actually switch to writing on the screen. Okay, so what do I want to start with? I wanted to start with quantum gravity. And quantum gravity introduces the fact that there is really a shortest distance. And to understand that, we see that in order to probe a distance d, as you know, in particle physics, or in just a relativistic world, to probe a distance d, I need very small wavelengths. And with very small wavelengths carry an energy which is of order 1 over d. Okay, of course, I'm using h bar equals 1 units. So we know that we need a lot of energy in order to probe short distances. That's why we build big particle colliders. But in the presence of gravity, if you concentrate a lot of energy into a small distance d, then there is the danger that you will create a black hole. Okay, so let me be more general and just say, so in the presence of gravity, you can form a black hole whose size, or the size of its horizon, is roughly given by g Newton times the energy that you've concentrated. So in general, I mean, often we just talk about putting some mass together in a small region to create a black hole, but you can put energy together, concentrate energy together, and you would create a black hole. And the danger is that in trying to probe a distance d, you might instead create a black hole which is bigger than d. Okay, so you might fail to probe the distance d because you created a black hole which is even bigger than that. And you can see by putting these two equations together that this happens when d is smaller than the so-called Planck length, which is basically the square root of g Newton. Okay, so if you attempt to probe a distance smaller than the Planck length, then just putting these two things together, you see that in fact you end up creating a black hole which is larger than the Planck length. So this means that fundamentally there is in the presence of gravity, we can never probe a distance smaller than the Planck length, okay, which is about 10 to the minus 33 centimeters. So that means that even in principle, there is an ultraviolet cutoff on physics, or a shortest distance in that sense, okay? And there's also a kind of heaviest mass for point particles. Okay, so particle physics is the study of point particles or elementary particles. And we mean that they're point particles if their Compton wavelength, which goes like 1 over m. We want to say that we can probe down to distances of order 1 over m, and then point particles will behave like quantum mechanical point particles. But again, in the presence of gravity, there's a danger that if the mass is too big, then instead of looking like a point particle with a Compton wavelength, it will look like a black hole again, okay? So if, in fact, if m is bigger than the so-called Planck scale, which corresponds to, say, 1 over square root of g Newton, okay? If the mass is bigger than that, then again, there is a Schwarzschild radius or black hole radius that is roughly up to factors of 2 or g Newton times m. And this is bigger than lambda Compton. Which means that if a particle mass is bigger than the Planck scale, instead of looking like a quantum particle, it will look like a classical black hole. Okay, its Schwarzschild radius will actually be large, and you won't see the quantum mechanical nature of the point particle. Okay, so for both of these reasons, we can conclude that there's a kind of ultraviolet cutoff, lambda UV, I'm going to write it as, which you can say in energy, it's lambda UV, or in distance, it's a shortest distance scale. And it must be, this ultraviolet cutoff must be smaller than the Planck scale, which is again roughly 10 to the 18 to 19 GeV. And this is the cutoff. It is the cutoff of the standard model, well, it's a cutoff of particle physics. So if we're trying to say what is the regime in which particle physics exists, well, it can live at very small masses down to essentially zero mass, like the photon or the graviton, and it can extend all the way to the Planck scale. But above the Planck scale, it's not really particle physics anymore. It's really sort of black hole physics or gravitational physics. But in this big regime, this is a huge regime between massless photons and the Planck scale, this is the proper range in which particle physics can take place. Okay, so this is sort of the physical limits. But it's important to realize that, here, let me just get another, that in renormalizable quantum field theory, we actually, okay, the whole art of renormalization and the understanding of it is that in the renormalizable theory, we may introduce a cutoff. We may introduce an energy or momentum cutoff. But ultimately, we take it to infinity. Okay, so it's an intermediate step that we put in a finite cutoff. We do some calculations, we do some renormalization, and then we find we can take the cutoff to infinity. And we don't depend, therefore, on what's happening at the cutoff, if you like. But in truth, but that's not the rule of the real world, because the real world contains gravity. And so what we're really saying in the real world is that this is just an approximation to the truth, where lambda UV, because of quantum gravity, if you like, okay, where lambda UV is actually finite, but very large. Okay. So in that sense, renormalizable quantum field theory, as you've been learning it, is actually a kind of approximation to the real truth. Okay. And mostly because we live at much lower energies than the Planck scale, this aspect doesn't matter, but it's definitely worth keeping in mind. Okay. So again, just to flesh out the perspective, I think it's worth, of course, many of you know or have heard that string theory is a theory of quantum gravity. And indeed, it's the best developed theory of quantum gravity that we are aware of. So because of that, I want to make a kind of analogy, just so you know, again, most of my lectures are not about string theory, but where does string theory fit in the backdrop, in the background of everything that I'm talking about, or any theory of quantum gravity, but in particular, let's just keep string theory in mind. And I sort of want to make a quick analogy, which I think will be useful in what we are talking about going forward. So I want to parallel it with the standard model of particle physics. Okay. In fact, more generally here, let's erase this and say with the electroweak theory. As put the renormalizable electroweak theory, which is part of the standard model. So here's my analogy. So let me just divide it up here and sort of talk about quantum gravity on this side, and here the electroweak physics. And so first of all, you can ask about the coupling constant. The coupling constant of gravity is g Newton. And by this, I mean its dimensions. Okay, so the engineering dimensions of g Newton is -2. And the engineering dimensions of g Fermi, which is the coupling constant of the weak interactions, is also -2. And of course, negative dimension coupling constants is what we mean by, I mean, or is the hallmark of being non-renormalizable. Which means it does not behave well in the ultraviolet, but it is a reasonable theory in the infrared. Okay, so that's one aspect to keep in mind. Then there is a maximum scale. Let me just say what I just said, that there's a kind of maximum scale where these non-renormalizable theories are valid too. So we just talked about lambda UV in quantum gravity being smaller than the Planck mass. And this is sort of m Planck or so. And here in the Fermi theory, it is less than the so-called, or the square root of G Fermi, which is what we are calling the weak scale. Okay. So in each case, these two theories, general relativity as a quantum theory and Fermi's theory of the weak interactions as a quantum theory, they are useful, but they're limited by these ultraviolet cutoffs. Okay, they're restricted by that. There's a shortest distance to which they're valid. Then there's sort of string theory, where particles are really seen to be strings with a typical length L string. And there's a mass scale, which is where particles are seen to be stringy. There's an energy scale at which their stringiness becomes evident. Okay, and it's smaller than the Planck scale. And on the electroweak side, there's the electroweak theory of Glashow, Weinberg, Salam, Higgs, etc. And there's something analogous, which is the W boson, and it's smaller. It's a little bit smaller than the weak scale. And there's a perturbative theory of string theory where there's a G string, which is smaller than 1, and therefore you have a kind of perturbative expansion. And here there's a perturbative couplings in the electroweak theory, which are also smaller than 1, and so you have a perturbative theory of that sort. And basically, when you get to energy, as you're doing low energy experiments, as you get more and more energetic, then something dramatic happens when you hit these mass scales, MW or M string. The theory changes radically. So instead of being general relativity and the weak and Fermi's theory, you end up with string theory and the electroweak theory at high energies when you're above the mass of the W or above the mass of the strings. Okay. I didn't mean to make this look like a ratio, so I'm going to just erase that. Okay. Okay, and now there's one place where there's a distinction, so I'll write that in red in this analogy, that above MW, or there are shorter distances. So the concept of distance makes sense in the electroweak theory to arbitrarily short distances. But in string theory, they're even with strings, there is a shortest distance. Okay, so there the distinction breaks down. Just as a backdrop, I think if you want to just see a quick lightning introduction to string theory, which I think is useful, there's Witten's ICTP colloquium, I think is a YouTube video. You can get it, which is called, well, I'll just say it, which I think is in 2023. It's just called What Every Physicist Should Know About String Theory. Okay, great. So fine, that's the backdrop to that. And the main takeaway is that there is really some sort of an ultraviolet cutoff somewhere below the Planck scale. So if I go back to the spectrum of particle physics, here are the mass scales. So here's the Planck scale of whatever, 10 to the 18 GeV. that we just talked about. Black hole physics is above that scale. Particle physics is below the scale. Um, and just from, before I did it on a logarithmic scale, I used a log scale to do masses. But if I used a linear scale, then of course it would look like this. The standard model would be here, right? Sort of below of order 100 GeV. So if you just look in the most coarse-grained way, you would say that a lot of the hierarchy problem is simply this picture that I'm showing you here. And you could say from the perspective of this picture, you would say this is all approximately massless. Okay. On this scale, even 100 GeV is nothing. And so one of the mysteries is simply why is this so close to zero? Why is the standard model so near zero on the scale of the natural range of particle physics? And the beauty of the standard model is that it reduces that mystery. It doesn't answer the mystery. Why is the standard model so light compared to the natural scale of particle physics, the dividing line between particle physics and black hole physics or general relativity? But it at least reduces the mystery. And so that's what I wanted to go into next. Okay. And the key feature is that the standard model, which you've been learning about, I gather, in the main part of this summer school, the standard model is a chiral gauge theory. So in order to talk about its chiral nature, I just want to remind you of like what's called the Weyl or chiral basis for the Dirac matrices, okay? Because again, you may know this well, but just in case, so that we're all using the same notation. Of course, the Dirac matrices have to satisfy the Dirac algebra, which is the anti-commutator is 2 eta mu nu, where this is the Minkowski metric. And this metric is, in the way I do it, is +1 and then -1, -1, -1. Okay, mostly minus signature. But in the chiral basis, gamma 0 is basically this. I'm using 2x2 blocks to represent these 4x4 matrices. The spatial gamma matrices are just the Pauli matrices. And the gamma 5 matrix thrown in is this. And in this basis, a spinner, in a 4-component spinner, can be written as a 2-component spinner, which is psi left, and 2-component spinner, which is psi right. And you can project either of these by just applying one minus or plus gamma 5 over 2, right? So by using this projection matrix 1 plus or minus gamma 5 over 2, I can either pick out the first 2 components or the second 2 components. This is psi left and psi right. And the significance of these 2 components is that each of them undergoes Lorentz transforms into themselves. Okay, so psi left and psi right don't get mixed up under Lorentz transformation. Psi left transforms into another psi left and psi right into another psi right. And that's easy to see because, again, just in the standard development of spinners, Lorentz transformations on the components of the spinner are, or if you want, infinitesimal generators. Are given by the matrices sigma, capital sigma mu nu, which are up to some constant, just the anti-commutators, sorry, the commutators of the gamma matrices. Okay, so since it's antisymmetric, there are 6 of these sigma mu nus. They correspond to the boosts and rotations. And as you can see, if you just think about it for a second, these anti-commutators of these gamma matrices, since the gamma mu's are off diagonal, the anti-commutators are diagonal. Okay, so these are going to be diagonal, block diagonal. They're going to look block diagonal. And hence what that means is that psi left will be rotated into another psi left, psi right into another psi right. Okay, so that's so just to say that again, it means that they're going to be something here and something here, but zeros off diagonally. Okay, so that's the significance of the sort of these chiral fermions called psi left and psi right. Okay, so let's see why that's significant. In that language where we can now use these 2 component spinners, q psi left and psi right, we can look at the quantum numbers. So standard model has, you know, I'll just call it strange quantum numbers, quantum number assignments. So let's see who they are. So there are 3 generations, as you know, and each generation looks, as far as the quantum numbers are concerned, each generation is a copy of all the others. Okay, so they're all just 3 copies of the same thing. So let's just look at a typical, like say the first generation. The first generation has the so-called left-handed quarks, which is a combination of the up left and the down left quarks. So each of these has got 2 spinner components, right? Because we're working in these 2 components language. And it's equal to, so we usually write it like this, where the notation is that this is a QCD, a triplet of QCD, which is to say it's 3 colors of QCD, which we'll talk about in a bit. And this is what's called weak isospin. And so this is under SU3, the SU3 gauge group. It's a triplet. Under the SU2 weak gauge group, this is a doublet. And this is its hypercharge, which is usually just written as Y. Okay, so that's the notation. And so there's that thing. Then let's quickly scribble down the rest. So we can write, U right is a 3, it's a weak singlet, and its charge is its hypercharge. And D right similarly has minus a third charge. There's the left-handed leptons, which are the neutrino and the left-handed electron. And these are singlets. They don't transform under QCD, but they are doublets of the weak isospin. And they have hypercharge like this. And then E right is a singlet of both non-abelian groups, and it has negative charge. Okay, so the key point of writing all this down first is that we see that the SU3 cross SU2, cross U1 hypercharge gauge symmetry of the Standard Model forbids any fermion masses. And we can just see why, because again, I'll just use the standard type of mass term, but we'll generalize it later. So this is the typical kind of mass term you first learn about for fermion, psi bar psi. And if you write, but this is written in terms of four-component notation. If I break that down into two-component notation, this is psi bar left, psi right, plus psi bar right, psi left. And you can see that with this set of quantum numbers, you cannot pair up any psi bar left with any psi right and have something that can be invariant under the Standard Model. For example, if I take the left-handed quarks and say one of the right-handed quarks, then you see that even the hypercharge will not cancel. It will not be invariant under hypercharge. It will not be neutral under hypercharge. Okay, so this is a beautiful feature of the Standard Model, that just the gauge invariance forbids any kind of fermion masses. So as long as this gauge invariance is intact, the question, why are the Standard Model fermions so much lighter than the Planck scale, is answered. In fact, they have to be massless. Okay, and similarly, if I ask, what about the gauge bosons of the Standard Model? Gauge invariance obviously forbids gauge boson masses. In that some gauge boson mass like this violates or is not invariant under a gauge transformation. Even the simplest abelian kind of gauge transformation fails, right? So we understand in one shot why almost every particle in the Standard Model is massless, as long as we have this symmetry. The symmetry, the gauge symmetry, explains why the Standard Model is massless. And the gauge invariance itself is needed for the self-consistent interactions of these massless spin 1 particles, the gluons, the electroweak gauge bosons, and the photon. If they are massless particles, then you need the gauge invariance. So gauge invariance tells you why the Standard Model particles are massless, and having light Standard Model particles, including spin 1, requires gauge invariance. They go together. Okay, so it's a nice tight qualitative understanding. But it does, well, of course, in a sense, these quantum numbers that are assigned here do seem puzzling at first. Okay, I mean, not puzzling. You're just curious who chose these quantum numbers. Okay, of course, you know that there is there are masses for many of these particles do get masses, and that's because there's also the Higgs field or fields, H, which under this classification are uncolored singlets of color, a doublet of the weak isospin, and they have, I think in standard notation, hypercharge half. Okay, and now we see why that's important, because they can so this vacuum expectation value, right? Normally written like this, or just like this for short, that this can break the gauge symmetry. So again, I'm guessing you have studied this in your regular lectures. So it's a two-component isospin. It's a scalar, but it's a doublet of isospin. And any expectation of this two-component field, by using the SU2 gauge invariance, you can rotate it to take this form. Okay, and this so-called weak scale is about of order 100 GeV, or I guess exact number is 246 GeV. And you can see that there is a subgroup. So this thing breaks spontaneously or through the Higgs mechanism. It breaks the electroweak gauge symmetry. And but it preserves electromagnetism. Well, it's a subgroup of sorry. As you do weak cross U on hypercharge. Okay, so and you can see that where this generator, the generator of electromagnetism called electric charge, is where you combine a hypercharged rotation with the third weak generator of SU2. Okay, the diagonal generator of SU2, which for a doublet, of course, I just mean that this is a half minus a half when it acts on a doublet. Okay, so if you put those together, then given this assignment here, you can see that this VEV preserves electromagnetism, but it does break the SU2 and it does break the hypercharge, but it preserves this subgroup. Okay, so in this way, as you know, again, you will have studied it, that, but let me just say it here, that couplings of H, of the Higgs field, to fermions and gauge bosons then lead to masses. Okay, so the masses are forbidden by gauge invariance, but once the Higgs breaks that gauge invariance, we generate masses. Okay, but that means that in one shot, there's sort of one miracle that's still unexplained, but then we're already doing better. That is, if this is our picture of mass scales, now they're not exactly zero. The standard model is down here. But what it does tell us, and maybe I should have said it here, and these masses are less than or comparable to V weak, because the couplings of the Higgs to fermions and gauge bosons, G standard model, the couplings are all sort of smaller than 1. And so you generate masses which are G standard model times the weak scale, which could be as big as the weak scale, for example, in the case of the top quark, or really tiny like the electron mass. But in that sense, we understand that everybody is capped by the weak scale. So once I just explain that the Higgs gets a small vacuum expectation value, or VEV, then in one shot, I know that all the particles of the standard model must have masses that are smaller or comparable to that scale. So in some sense, there's a single mystery in this picture of why is the Standard Model so much lighter than the Planck scale. We could say that there's a single mystery of why the weak scale is so small, right? Why is V weak? Okay. Um, but indeed, just to sharpen this slightly, uh, this is related to what's called the hierarchy problem. And in a sense, I've been talking about a hierarchy problem the whole time, right? I've been saying that the puzzle in particle physics on a big scale, the puzzle is why particle physics is so hierarchical in structure. The more we look at it in detail, we'll see the more and more hierarchical aspects of it. But one root is now by the chiral gauge theory structure of the Standard Model, we've already concentrated one question, which is a single mystery. Why is the weak scale much smaller than the Planck scale? And this is literally what is called the hierarchy problem. Um, Although really there are a number of others, but this is the one that's given this name. And we can sort of study a little bit. We're sort of close. We feel close to understanding why there are so many hierarchies. If we could just understand this hierarchy, why is the weak scale small? Um, and of course, if you again recall the Standard Model structure of the Higgs, you know that the Standard Model has a potential for the Higgs, and it's usually written minus mu squared. So this would be a mass term for the Higgs, except that it's got the wrong sign to be a mass term, right? It's like a negative mass squared. So it's usually written minus mu squared, plus a quartic interaction like this. And so we're used to picturing that, giving us the so-called wine bottle potential. Where on the horizontal plane, I'm trying to draw the Higgs. Of course, the Higgs is two complex scalars. I only have one complex plane that I can draw it in, but this is the usual wine bottle potential with which I think you're familiar. And indeed, this tells you that the ground state has to live on the rim where you have non-zero Higgs field, and you can rotate it into a kind of canonical form like I did in the previous slide. And the magnitude of this VEV away from the origin is the weak scale. Okay. So roughly speaking, this mu is the only mass term. The mu is the only mass term explicitly in the Standard Model Lagrangian. All the other couplings that you see in the Standard Model are dimensionless. But this is the origin of, at least classically or at tree level, without worrying about subtleties, which we are going to come to, naively, this is the only origin, this is the only mass scale in the Standard Model. Okay. And this is again, it's of order. Oh, sorry. It's of order. It's of order 100 GeV. Okay. Again, that's the going rate, the so-called weak scale. Great. So let me see what I want to say. Okay. But one aspect that, again, you may have heard of with the hierarchy problem is why is the well, it's to do with radiative corrections or to do with quantum loops. At the moment, the question is, why is this mu, or why is this mass parameter of the Higgs potential, why is it so small compared to the Planck scale? And normally you could say, well, it just is. that's the way it is. Okay. Now it gets trickier when we consider radiative corrections or loop corrections. So for simplicity, just to get us started, I will just consider, instead of something as subtle as the Higgs, I'll just consider phi to the fourth field theory, where we just have one scalar rather than two complex scalars. Let's just think of one real scalar, and right, let's just look at it like this, right? So this is standard phi to the fourth field theory. This has got the proper sign for the mass term, so there's no spontaneous symmetry breaking, but it shares many features with the Higgs theory in that it's a scalar field theory. And now we can ask, let's just do the dumbest kind of loops that we can do as we watch the propagation of this scalar field, right? So this is the usual I over p squared minus m squared plus I epsilon. There is the propagation of the scalar field phi. Okay, and remember, phi is our toy model for the Higgs field. But when I have loops, there's a correction to that, which looks like this, where I can use this quartic self-interaction to make a loop like that. And in fact, I can, at higher loops, I could do things that look like this. Okay. And now I'm going to keep it maximally simple. So I'm just going to keep writing terms that, well, let me just call it ellipsis for the moment. So if we just focus on this guy here and just say, what does this now look like? So of course, here I've got two propagators on either side. And I now have to do this loop integral, and this thing will look like something like the vertex will have a minus I lambda. There will be an integral d4p for the loop momentum p over 2 pi to the fourth. And then there's the internal propagator I over p squared minus m squared plus I epsilon. Okay. So to do this integral, first of all, you can see it's not very well behaved, right? But we have to keep in mind that we're really doing this in a theory with quantum gravity. There really is a shortest distance. So that's not apparent in this calculation. This calculation here does not know that there is a world of quantum gravity out there and that quantum field theory itself, renormalizable quantum field theory itself, is just an approximation. There has to be an ultraviolet cutoff somewhere. So in some way, the ultraviolet cutoff that is got to be there in a world of quantum gravity has to cut off this integral and make it well behaved in the ultraviolet. Now, in fact, if you just cut off the momentum, the spatial momentum, for example, then in fact you could do this integral by Wick rotating p naught to IP4 and getting a Euclidean integral, an integral that looks like Euclidean four-dimensional space-time. And then you wouldn't have to worry about the irritating signature of Minkowski space. So that Wick rotation is not justified in the complex plane for the P0 complex plane. You can't do that Wick rotation that we often do with Feynman diagrams because of the bad behavior in the ultraviolet of this integral. However, we're granting ourselves that something in the ultraviolet must tame that bad high energy behavior. I'm calling it lambda UV, in which case we can do the Wick rotation, and then you can quickly estimate what this diagram is going to be, and the answer will come out to be, keeping the factors of I, this, that, and the other. It'll be minus I lambda over 16 pi squared, coming from all those 2 pi's and integrating over angles. And then, but it's going to depend on how we cut it off. Okay, just by dimensional analysis, you would have guessed that would be true, that whatever this ultraviolet cutoff is, it's going to set the scale for this divergent, ultraviolet divergent calculation. And now here, it looks like I'm going to get 2 copies of this loop integral. And if I kept going here, I could get 3. And then, of course, there could be other more complicated diagrams, but at the very least, this. And at least this one, we can see how to resum the geometric series that we have here. And this would look like I over p squared minus m squared minus lambda over 16 pi squared. I should say, if you did this integral, there would be corrections which are order m squared. But let me just keep the cartoon here and say lambda UV is the biggest scale. So it's approximately given by dropping the order m squared terms. And so by resumming the geometric series, I would get this. And this would say that there is a so-called corrected effective potential by taking into account these quantum loops. The effective potential is really not just the original potential, but m squared plus lambda over 16 pi squared lambda UV squared times phi squared, and then plus the lambda phi to the 4th. Okay. So it looks like quantum mechanics has corrected the potential. And of course, this is I've done this example. It's one of the simplest things to resum in that way. I've dropped diagrams. Which could look more complicated at higher order. So there's a whole systematics of what is the dominant contribution to the effective potential, which I'm not going into. But the upshot is that the effective potential gets corrected, and in particular, the mass term is corrected in a big way because of this large ultraviolet cutoff. You could say that this is sort of an m squared effective. Okay. And you can see it's the sum of these 2 terms, right? So similarly, in the electroweak theory, with the Higgs, quantum mechanical corrections will typically look like, so some function of standard model dimensionless couplings times lambda UV squared. Okay, so instead of just little lambda in my toy example, it's at higher loops, it'll generally be some function like this over 16 pi squared, where this f is some function of dimensionless couplings in the standard model, and it starts at order 1 and gets smaller as you go to higher order in perturbation theory. Minus mu squared. Okay, so that the minus mu squared was already there, and then we have these loop corrections, and then plus some lambda h to the 4th. Okay, sorry, I should have squeezed in. Okay, and so this term here we could call it a minus mu effective squared. And we know that this, just from experiment, we know that this is order 100 GeV, right, squared, if you want. Whereas we are expecting this to be order m Planck, which is 10 to the 18 GeVs. So the only way this could be true is if the original mu, not mu effective, but the original mu, if these two terms are somehow canceling to give this very small result. So this fine cancellation, or tuning, is the face of the so-called hierarchy problem. Which says that, especially taking into account these quantum corrections that we expect are there and that are cut off by some ultimate ultraviolet cutoff of quantum gravity, that it seems strange that these enormous Planckian numbers should cancel so finely to give this very small 100 GeV. And this is to be compared with the rest of the standard model, where if you didn't have the Higgs, the rest of the standard model, it's beautiful. Why are the particles so light compared to the Planck scale? Well, chiral gauge invariance tells you they must be exactly massless. Now, I know that they have masses, but at least at the cartoon level, being massless is a complete explanation of why you are much lighter than the Planck scale. Whereas as soon as you put the Higgs in to try and give small masses to all of the other particles, as soon as you put in the Higgs, you find that the Higgs effective potential itself is tuned in this sense. That is, there's no understanding why the Higgs VEV is order the 100 GeV scale and is the result of an enormous cancellation between Planckian quantities in the top line here. Now, I've said this in perhaps the most naive way I can, where I've talked about ultraviolet cutoffs and things like that, which normally nowadays people would not say it in quite this language, but I'm being deliberate. I know that in calculations like this, I'm being just a tiny bit sloppy. I didn't include all the diagrams. I just included the diagrams that are easily resummed as a geometric series. And there is some way of thinking about what is the most important corrections. And indeed, these are the most important corrections to the effective potential. So I'm not going into all of that, but I'm also saying this idea that lambda UV is a cutoff, and that this cutoff really represents something like string theory, right? It's the scale at which particle physics ends and the stringy behavior of these particles. The particles are secretly not point-like, they're secretly strings on short distances, that takes over. So you might ask, in this kind of rather lowbrow or very naive way of cutting off Feynman diagrams for point particles, am I being true to the way that string theory works? Because if you know anything about string theory, you'll see that the way it tames ultraviolet divergences is a very subtle and beautiful thing, as well explained by Witten in those ICTP, that ICTP colloquium that I advertised, or in any string theory textbook. It's a much subtler kind of thing than just throwing in a cutoff in your calculation in Feynman diagrams. So maybe there's some magic to it. Maybe there's some magic by which the cancellations that we're seeing on this screen here are just not like the way it looks here. Okay, maybe there's some magic to it. And people have speculated about that. But I would say today, nobody has convincingly explained how the quantum gravity cutoff, let's call it the string scale, magically allows you to avoid this kind of tuning that we're seeing here. So it remains a puzzle. And I'm not apologizing, therefore, for invoking this cutoff and just saying that this is a kind of puzzle that we call the hierarchy problem. Now, if you're feeling vaguely unsatisfied that the thing you understand least, the physics of lambda UV, the physics of quantum gravity, is being invoked to say that there's a problem, then that's okay. You be a little bit uncomfortable because I'm going to give examples of solutions to this problem. And when you see the solutions, I hope you'll see that the solutions are so stunningly beautiful that they make you embrace the problem and say, ah, it was worth calling this a problem because it led to me seeing something beautiful that could be taking place in nature and which has experimental implications. Okay, so that's how I want you to think for the moment. This is just a placeholder for, therefore, the beautiful things to come. Okay, so I want to switch to the other puzzle that I brought up with the standard model, which is where do all these strange quantum numbers with the 1/6 hypercharge for left-handed quarks and all of that, where do these funny quantum numbers come from? And again, at one level, you could just say, well, that's the way it is. Like, there's nothing more to say. That's the way the world is. But we get some real satisfaction by taking that question seriously in the context of what are called grand unified theories, or GUTS. And so I want to turn to that. And you'll see that this hierarchy problem and my story of GUTS are not, I've left you with the hierarchy problem. I haven't answered it. I haven't given you a beautiful mechanism that solves it, but I will. And to build some of the technology for that, we can also study this question of the quantum numbers of the standard model and within the context of grand unified theories. So I haven't forgotten the hierarchy problem. I'm just coming to it in a novel way. Okay, so for grand unified theories, I want to start by just the basic group theory, which again, many of you may just know, but I'm going to talk about groups which are of the SUN type, okay? So of course, the standard model has SU2, the standard model has SU3, but I want to now just talk about SUN, which is really the classic Lie group or continuous group that you could imagine. And the standard representation of it would be a field. If you want, you can think of it as some fermions. It's a field which has an index, and this index goes from 1 to n. So for SU3 color, then this is just the quark color, 1, 2, or 3, or red, green, or blue. But here there are n possible colors, or whatever you want to call it, n degrees of freedom, and I'm calling it psi I. And under SUN rotations or SUN transformations, these things transform in some way, which I'll write like this. Okay, and in general, I'm not bothering to write summation over repeated indices. So I'm sticking to the usual notation where the repeated index is being summed. Okay, so I'm just telling you once, but in general, I won't keep repeating summation signs. And so we get this. And of course, the thing that defines SUN, and any matrix transformation has this form, but the thing that defines SUN is that it leaves the complex length fixed, or the complex norm fixed, which, if you think of psi as a column vector, is just psi dagger psi, okay, which it leaves fixed because in matrix notation, this would go to U dagger if I just conjugate that, and then the psi itself goes like this. And so the condition for leaving this length invariant is that U dagger U, so has to be the identity matrix. Okay, so that's one feature of these SUN or unitary groups. The S in there is just the statement that we don't worry about the unitary transformations, which are pure phases. So we take the determinant of U to be 1. Okay, so these are the two defining features of SUN, and we can work out how does that constrain U. And the nice thing about continuous groups is you can think about doing a group rotation as a series of small rotations. Okay, so you do the same small rotation many times and it accumulates to a big rotation. So we can just consider the small rotations, which is to say doing nothing, where I is the identity matrix, so doing nothing, plus some small transformation where T is a matrix and epsilon is just the parameter that tells me epsilon is small. So it just tells me that I'm doing a small rotation. Okay, and the I is just there by convention. And it's easy to see that in order to satisfy this condition, working to first order in epsilon tells us that T must be Hermitian. Okay, and again, many of you know this, but for the record, here it is. And by using the fact that determinant of an exponential, okay, so to order epsilon, this exponential is the same as 1 plus I epsilon t, but I'm writing it as an exponential because I can use the standard linear algebra identity that the determinant of an exponential of a matrix is the exponential of the trace of a matrix. Okay, so that's just an identity. But now the fact that the determinant has to be 1 implies that the trace of T is 0. So these so-called generators of the group, or the infinitesimal versions of the SUN group, T, the T's are any matrix, n by n matrix, any n by n matrix which is Hermitian and traceless. Okay, so we can just maybe summarize by just this. Okay, so good. So again, many of you know that. So let's just count how many different types of matrices are there which are Hermitian and traceless. And so this implies that there are, again, you can do it, n squared minus 1 real possibilities. Okay, so these are complex matrices. So in just counting how many different independent matrices there are of the form T, I'm going to just count real things. So anything that's complex, I'll split it up into the real and imaginary pieces. But if you just look at a square matrix and you make sure that it's Hermitian and also traceless, then you can do this exercise yourself if you haven't done it and see that there's n squared minus 1. So for example, for n equals 3, which is the case of QCD, there are 8 gluons corresponding to 8 generators T. Okay, and the T, since there are 8 of them, are usually given, they're usually written lambda. Okay, there are 8 such matrices. So each of these is a matrix. And these are the so-called Gell-Mann matrices. Okay. And n equals 2, of course, n squared minus 1 is 3. And there are sort of 3, what should I call it? 3 W bosons, plus minus, and sort of 3. W3 is part of the Z boson. It's part of the photon, but just from the SU2 point of view, you'd just have an SU2 gauge theory would have 3 gauge bosons. And this corresponds to the 3 generators where the T's are the Pauli matrices, either written as sigma or tau, 1, 2, 3. Maybe I'll use little a here. Okay, and again, these are the Pauli matrices. Okay, so that's all the group theory that I want to start with. And now let's start looking at granunification in the form that was pursued by Georgi and Glashow, where they are imagining a sorry, there's one thing I wanted to say before that. Yeah. Yeah. So the thing I wanted to say first was there is the distinction between, so there's a so-called fundamental representation, which is the one, or it's the defining representation, which is the one I just talked about, psi I, okay, where psi goes to u psi, right, in matrix notation. But there's something closely related, which is the anti-fundamental representation, which, let me see what's the easiest way to write it. Yeah, so you can write it as chi with a lower index j, and if I think of it as so psi, I treat it as a column vector, and wrote psi goes to u psi, right, where u acts from the left because psi is a column vector. Here I can think of this chi as well, I can think of it as a column vector, but then I'm going to tell you how it transforms by telling you how its transpose transforms, okay? And so this is going to transform as chi transpose u dagger, okay? So if you want, you say, that's a crazy way to write it. Why don't you just think of it as a column vector and write what chi does? Well, that means that chi transforms as u star chi, okay? So this is the anti, it's the complex conjugate. It's like the anti-particle representation, right? So these are 2 representations which are very simple, but they're not identical. And they're both kind of fundamental. Which one you choose to call fundamental, which one you call anti-fundamental is up to you. But these are 2 possibilities. And so in particular, if you had something like chi I, psi I, summing on I, which in matrix notation we could write as chi transpose psi, then obviously it transforms like chi transpose u dagger u psi. And since this is the identity, this product is invariant. Okay, so by contracting or dot producting fundamentals and anti-fundamentals, then we can get invariance under SUN. Okay. Now, in general, these are distinct. So for SU3, the fundamental representation is different from the anti-fundamental representation. So, for example, in SU3, the fundamental representation we call a triplet or a 3, and it is not equivalent to the anti-fundamental representation, which we usually call 3 bar. Okay. But important to note that SU2, they are not distinct. That is, the 2 is essentially equivalent to the 2 bar. And this is just a simple exercise to show that if I write, so I'll use alpha to equal 1 or 2, the usual kind of isospin index, or spin index even. And if I write it as like this, that if this thing with the upper index is a 2 of SU2, transforming the way, the way I have here on the top right, then you can check that if this is the standard epsilon symbol, which is just a matrix -1, 1, 0, 0, that then if you multiply by this matrix, you simply get something which transforms as a 2 bar. You can check just using Pauli algebra that that's the case. So there's no distinction really between a 2 and a 2 bar. But in order to take a 3 to a 3 bar or an n to an n bar in general, you actually have to complex conjugate it. Okay. So psi would have to go to psi conjugate in order for it to become an anti-fundamental. Okay, very good. So now we can just go to the Georgi, Glashow, grand unified theory, which is a gauge group SU5. Okay, and the remarkable observation, well, one is an easier one, which is just that SU5 contains the standard model gauge group as a subgroup. And once somebody tells you that, it's not hard to check how it would work. So we can take these SU5 matrices or generators, the generators of these matrices, they're infinitesimal versions, and we can sort of divide the 5 components. These are 5 by 5 matrices, but we can break it up into 3 and 2. So there's sort of 3 here and 2 here and 3 here and 2 here. Okay. And the 3 and the 2 are the 3 and the 2 colors and isospins of SU3 and SU2. So in that way, we can see that the Gell-Mann matrices, lambda A, can be thought of as 3 by 3 matrices that live in this block. So they only act on the first 3 colors of SU5. SU5 starts with 5 colors, but QCD, the SU3 matrices, are only acting on the first 3 colors. And when I write lambda like this, I mean everything else is zeros. All the other blocks are zeroed out. Okay, so that would be how I could make the 3 by 3 Gell-Mann matrices. I can make them into 5 by 5 matrices by simply putting zeros in all the other blocks. And as you can see, they would just rotate the first 3 colors, and the last 2 colors are left alone. And similarly, I could take the Pauli matrices which are 2 by 2 matrices, and I could make them live only in the 2 by 2 block of these 5 by 5 matrices. And similarly, they will only rotate the last two colors of SU5 and leave everything else alone. So it's super easy to see how SU5 contains as a subgroup SU3 and SU2. Okay. But then there is the hypercharge that we'd like to identify. And we can see that there's a very beautiful, simple matrix. Okay, so in these SU5 matrices, which are, remember, all possible Hermitian matrices, as well as the constraint that they are traceless. Okay, so certainly since the Gell-Mann matrices and the Pauli matrices are traceless, we've satisfied the tracelessness condition. They are Hermitian, so we've satisfied the Hermitian condition in this way. So what can we do about hypercharge? And so we can notice that I'll just give myself another copy, that in this split that I could have, I think the way I want to write it was, yeah, -1, -1, -1, 3/2, and okay, and zeros everywhere else. Okay, so consider this diagonal generator. Notice that as far as it's acting on in the 3 by 3 block, it's proportional to the identity matrix, right? Which means that it commutes with the Gell-Mann matrices. It's something completely separate from the Gell-Mann matrices. It's just doing nothing on or just rotating a phase. If you do 1 + I epsilon times this matrix, it's just a phase rotation on the 3 colors. And if I look at the 2 by 2 block, again, it's just some sort of rotation by a phase on the 2 by 2 block. And it commutes with all the Pauli matrices. Okay, in each block, it's just the identity matrix. So this is, in other words, it's a candidate for this U1 here, okay? Because then saying that you have a product group like SU3 cross SU2 cross U1 means that the generators in different factors have to commute with each other at the level of infinitesimal generators, okay? And that's exactly what this generator that I've written down, this diagonal generator, does. So we can guess that we can call this diagonal generator the generator of hypercharge. So we'd be tempted to write that this is equal to the hypercharge generator. And indeed it is, but for a very tiny subtlety, which I'm about to say, it is, okay? So the subtlety is simply the normalization. If you want to be quantitative, which we will want to be in a second, there's a small subtlety that if you just take the standard normalization of these we should treat all generators democratically. In SU5 takes any SU5 generator into any other SU5 generator. We should treat them democratically in our notation. So we all know that trace tau A over 2 trace, if you just look at this kind of inner product of generators, right? What the trace of these different Pauli matrices are, it's of course delta alpha beta over 2. Okay, so they're sort of normalized generators, so that if you take the trace of a product of generators, you get 1 or 0 times a half. Okay, so it's normalized to a half. So you can see that the generator I've written down as my proposed hypercharge is not actually, like if I look at trace of this matrix squared, trace of y squared, I'm not going to get a half, okay? But I can easily fix that by just changing the overall constant. And so that is this rather strange looking root 15. Okay, so now if I check, I'll get 1 squared, 1 squared, 1 squared, 3, and 9, yeah, I think you can check that this thing has the same normalization as everything else. Okay. Good. So that's the generator that is the same normalization, the same norm, the same size as all the other SU5 generators I've given you. But even this is not correct. And we'll see that the beautiful normalization of hypercharge that I just wrote down, which has the same normalization as every other matrix I've written down, is not exactly what we call hypercharge. Actually, what we call hypercharge, there's this extra root 3/5, okay? And this is simply a historical accident. As you're going to see, the fact that we said that the electron has charge -1 means that in this SU5 theory, there's this extra root 3/5. If the electron had charge root 5/3, if we were perverse enough when we discover the electron to say, I'm going to call you root 5/3 charge, then that would have fit very nicely with grand unification notation. But of course, nobody had heard of grand unification in the 19th century. Okay, so we'll keep track of why, where this comes from. But there's a standard model sitting inside. Now you see it. So if you really want just to write it separately, if I just solve for y, putting in the root 3/5, y is now got a simpler form. It just looks like -1/3, -1/3, -1/3, half, and -1/2. Okay, so that has fewer square roots in it, and that will be something you'll recognize soon. Okay, so you can see that out of the 24 generators we'd expect of SU5, we've accounted for 12 of them, namely the standard model generators. There are 12, but that means there are 24 extra generators that are missing, and you can see where they are quite easily. There is this block here. So this X is sitting in a 3x2 matrix. So X is a 3x2 matrix in general, and it can be complex. So X is a 3x2 complex matrix, or it corresponds to 12 real degrees of freedom. And as long as I put X dagger on the bottom part, then that's a Hermitian matrix, right? Because it's off diagonal and there's an X and an X dagger. So that means that these X's are any 3x2 complex matrices. Okay, so these are generators, and in SU5, of course, these generators correspond to gauge bosons. So these are gauge bosons that are part of SU5, but are not part of the standard model. But it's exciting to contemplate that the entire standard model set of gauge groups, of their strange gauge groups, are really coming out of something as simple as SU5. Okay, so that's the core idea of grand unification. Okay, so the question is, how does everybody that we know and love in the standard model, how do they transform under SU5? Okay, so let's see. So you could say, let's hope for the simplest thing. Let's hope that that fermions could be in the so-called fundamental representation, the 5 of SU5, right? That's a very simple representation. That's the defining representation of SU5. So we can hope that that's the case. In which case, psi would equal, if you break it up into 3 and 2 components, there'd be a 3 here and a 2 here, right? So again, let me just use a different color. That's not 3/2. That's just the dividing line. Okay. So it would mean that it would break up into, like, if we looked at it, if we looked at the 5 of SU5 with standard model eyes, then we'd say that this psi is equal to, well, there's a color triplet sitting there, but it's a singlet of weak isospin, right? It's not you can't, in this defining representation, if you're a triplet, you're not a doublet. And if you're a doublet, you're not a triplet. Okay, so it's this, but it's also a doublet. Okay. Now, yes, let me see. So one question is, we don't know what are the hypercharges? What are the hypercharges? Well, that's easy to see by just going back here. Since I know how hypercharge acts, it's very easy to see. It acts like -1/3 on the top, and oh, sorry, I made a mistake here. This should have been, sorry, it's a half and a half. I mean, it's proportional to the identity matrix, remember? So it's a half and a half. So the hypercharge is -1/3 on the triplet, and it's a half on the doublet. So we can actually fill that in here. We know that this is -1/3 and plus a half. Okay. And so we've made our guess. We can just ask, who could this be? Who could this be? And you see, it doesn't seem to quite match anybody we know. We do know that there are electroweak singlet quarks like U right and D right, but they have hypercharge +1/3, whereas this is hypercharge -1/3. But also, we know that the right-handed quarks transform differently from the left-handed quarks or the left-handed fields. So it's also hard to see how to put them together, because this, if you want something that's a color singlet, a color triplet, but a weak doublet, this should be sort of right-handed in the standard model. Whereas if you want something that has electroweak doublet, then that would be something left-handed. So how would I put different representations of the Lorentz group into the same thing? And fortunately, this idea that there's left-handed and right-handed is really a kind of convention and not essential. So let me just say that while right-handed fields and psi left-handed, right, left-handed fields, indeed, they do transform differently. So of course, this question of how to identify who is coming out of SU5 is puzzling us, but just to come back to this, psi right and psi left transform differently under the Lorentz group, right, which of course is SO3, 1 or SO1, 3. But they are very simply related to each other. So, but what's called psi right conjugate, where again, if I take this index alpha, this is the two components, this is the Lorentz index, this is the spinor index, and I use an epsilon tensor to relate it to so by just conjugating, right, complex conjugating a right-handed field and then multiplying by this matrix that just interchanges the indices with the up to signs. By doing that, I get this thing that's called psi right conjugate. It's called conjugate for obvious reasons. If it was a scalar, there would be no indices to talk about. You're just complex conjugating. Here, you have to also multiply by this epsilon tensor. And then you can show, this is again just given the algebra that we've already talked about, defining left-handed and right-handed. You can show that this transforms exactly under the Lorentz group. It transforms exactly as a left-handed field. Okay? So in this sense, again, you may or may not have come across this before, but all right-handed fields can be re-expressed as left-handed fields by just working in terms of the conjugate, psi right conjugate. Okay? And that way we have a uniform treatment of all the fermions in the standard model. All of them are simply left-handed fields. So we will use all left-handed spinors from now on, or spinors or spinor fields. Okay. And this is just the generalization to the Lorentz group of what I said with SU2. With SU2, remember I said doublets and like the 2 and the 2 bar are secretly the same, right? Here, left-handed and right-handed are almost the same. They're charge conjugates, and then you have to multiply by this matrix. Okay, so the multiplying by the matrix is exactly how the 2 and the 2 bar were related in SU2. Okay, so this is SO3 comma 1 is a bigger group. You also have to do the charge conjugation. Okay, so we can switch to all left-handed notation. And in that, we can rewrite all the standard model fields. They're all some sort of left-handed fields. And there's Q left, which hasn't changed. It's still a 3, 2, and 1/6. And there's U right. But now I'm going to use left-handed notation. So U right conjugate is actually a left-handed field. Okay? But because I'm conjugating it, in particular, the complex conjugation takes the 3 to a 3 bar, right? So it's an anti-triplet, still a singlet of SU2, and the charge, because I complex conjugated, I get the opposite charge, which is minus 2/3. And similarly, D right conjugate is 3 bar 1, and now it's plus 1/3. Okay, and then the leptons, again, there's the left-handed lepton, nothing has changed there, which is 1,2 and minus a half. And then there is the right-handed electron, but now it's the left-handed electron conjugate, okay, or E right conjugate. So I'm in this notation, everything you see from now on is always a left-handed field. Whether I write right or left, it's just to remind you about the quantum numbers. They're all, in terms of Lorentz transformations, left-handed fields. So this is +1. You can think of it as the positron field, okay, +1. Okay, so now we can see how to try and identify who is the 5 of, so if we take a look back here, we see that, where to go, that the 5 contains this triplet you can see on the top right corner. It contains something with it's a triplet, but with hypercharge minus a third. Whereas if I look at the triplets, which are not doublets of electroweak, if I look at the triplets, they're actually anti-triplets with hypercharge minus 2/3 and 2/3. So in fact, this, we can see that that in fact in the 5-bar representation, where you would have a 3-bar and a 2. Again, I don't write it as 2-bar because 2 and 2-bar are the same thing. So I'll just write it as a 3-bar and a 2. That this thing fits in a, like being a D-right conjugate plus, so maybe I should write it like this. It's a D-right conjugate and a left-handed doublet, which is not colored, okay? So you can see in the conjugate representation, this would be a 3-bar, and just the hypercharges, you can see that in the 5-bar, the hypercharges would be the opposite of a 5, right? So the hypercharges here are -1/2 for the lepton and +1/3 for the D-right conjugate, and you can see that's what you're seeing here. That if you take the conjugate of this y, or the opposite of this y, it's +1/3 and -1/2, and that's exactly what we're getting here. Okay, so fine. Some of the fermions of the Standard Model, remember, this is just one generation. There are 3 generations, but they're all got the same quantum numbers, the same puzzle of quantum numbers. So one generation of the Standard Model, say the first generation, you can see that the 5-bar, which is about as simple as a 5, does actually contain some of the fermions of the Standard Model. And but then there's a question of where are the rest of the Standard Model particles? There's 10 more Standard Model fields here, and where are they inside of SU5 representations? And so that gets just to a slightly more complicated piece of representation theory, which is that we can talk about you can also talk about tensor representation. If you have the fundamental representation, I can also look at product representation. So I can look at something which is, instead of being a 5, so that's a 5 in my notation, but this is a tensor representation, or a product of 2 of the 5 representations, by which we mean, just so we say exactly how does it transform, it transforms, each index gets rotated separately. So if you want, what we're really saying is that each index rotates like this, okay? And on top of that, we can insist, again, many of you may have studied all your group theory and know all this, and maybe you don't, but here it is. I'm telling you, this is a very simple way to transform, right? That each index transforms. But we can take these to be antisymmetric, meaning that chi ij is equal to minus chi ji, and you can check for yourself that that is consistent with this transformation law. Okay, so if chi ij equals minus chi ji, and then you do a rotation of this type, then this antisymmetry remains true. Okay, so if I count that corresponds, remember, these are 5 by 5. These are 2 indices, each of which range from 1 to 5, antisymmetric. That corresponds to 10 components. Now, we are looking for 10 extra fermions in the Standard Model. So the genius of Georgi and Glashow is that they could see that these are the 10 guys, okay? So let's see how that would work. So who are these 10 components? So we could have, for example, I equals 1 to 3. So we could have one of these things that are colors, okay? And then the second index could be another color, right? So this would be something which is, of course, but this would be minus chi ji. So it's an antisymmetric pair of colors. And you can see that epsilon, you can check for yourself that epsilon I, j, k, chi I, j, okay? So that leaves just one index k. transforms as a 3-bar. Okay. It's a bit like saying when you do a curl or a cross product. It's saying when you have a cross product of vectors in space, the cross product is another vector. So here you kind of got like this ij is like a cross product of two vectors, one with index I, one with index j. And when you do the cross product, instead of being a triplet, two triplets of color, you again get a triplet, but it's really an anti-triplet. If you're keeping track of triplet versus anti-triplet, it's an anti-triplet, and you can check that for yourself now. So we're expecting that this is the triplet, an anti-triplet. So that's good because we are waiting for some place to put the U-right conjugate, right? We want an anti-triplet place to put that. So that's good. And then we could also have something where you have a color index and an isospin index, right? Which I'm calling alpha. And that would be a, so of course it would not, there are no isospin indices here. This would be something which has got no color indices, but it is a doublet. Sorry, no, it's got a color index and an isospin index, so it's a 3-2. So that good candidate is the left-handed quarks. And then there are something like chi alpha beta, but if it's antisymmetric and it only has two indices, then secretly there's only one object there. Okay, there's only one non-trivial component. So that must be a singlet of electroweak and color. And I just leave it as an exercise. You can put in the hypercharges yourself to check who these guys are. And so this has got exactly the quantum numbers of U-right conjugate. This has got the quantum numbers of Q left, and this has got the quantum numbers of E right conjugate. And just remember that when you're looking at the hypercharges, you have to add the hypercharge relevant for this index and the hypercharge relevant for this index. Okay, you have to add them in order to get the total hypercharge for that field. And if you do that, you'll find that that fills in the hypercharges here that we get from the standard model. Great. So in this way, with two relatively simple, the psi I 5 bar and the chi ij 10, we find exactly the standard model charge assignments explained. Okay, so everything comes out of a much simpler type of group theory, namely that of the SU5 theory. And there's one more field in the standard model that is very easy to take care of, which is the Higgs field. Okay, so the Higgs field, like it's a doublet of it's not color triplet, but it's a doublet, but it can easily be incorporated into a 5, right? This just a 5. So I'm using curly H to represent this 5. And it's easy to see what to do. You would put, again, in the 2 and 3 split, you would put the Higgs doublet down here. And then something has to sit here, and it would be a colored Higgs, which, of course, we've never seen. It would have to somehow be so heavy that LHC hasn't produced it, okay? So there's a colored Higgs, and so this would be the usual 1, 2 plus a half that we would expect in a 5, and this would be a colored cousin of the Higgs, like that, okay? So of course there's a question, why is it missing? Okay, but we can come to that next time. And so in this way, we have sort of made the gut, the grand unified SU5 theory, contain the standard model. But so the remaining job for tomorrow is, so this gut contains the standard model, but must explain why don't we see the entire gut? Okay, we must explain why only standard model survives to low scales. Okay, very good. I think I've hit my time. I have plenty of stamina, but I'm going to guess that since you've been listening, that you're tired out. So maybe we pause today, take any questions you may have, and then take up the question of how did the gut break down to the standard model tomorrow. And again, secretly, I'm building some of the machinery to think about the hierarchy problem, which you might say, all I've been doing is group theory and so on. But secretly, I am getting us to where we want to talk about the hierarchy problem. Okay, I'm pausing now, and any questions in whatever format the organizers think appropriate, I can take. Thank you.